Single-photon avalanche diodes, or SPADs, are novel image sensors that are sensitive to individual photons and can record the arrival of photons with picosecond precision. Till a few years ago, SPADs were only available as single-pixel or small arrays such as 32 by 32 pixels. While they showed promising performance in lab settings, they were largely restricted to static and relatively simplistic scenes. Fortunately, the resolution of SPAD arrays has improved rapidly, which, for the first time, allows capturing high-frequency spatial details needed for general computer vision in the wild. But one challenge here is that SPADs capture a stream of binary frames with sparse detection of photons. It is nearly impossible to understand what is going on in the scene from a single frame. Therefore, we need to combine information from a binary sequence before we can perform downstream computer vision tasks. Existing SPAD cameras simply add binary frames captured over time into multi-bit images by using on-chip counters. Although this approach works well for static scenes, it suffers from the blur-noise trade-off. The result images are either too noisy or too blurry, and the downstream algorithm, for example object detection, fails to work. Inspired by burst photography for conventional cameras, it is possible to measure and compensate for the motion between binary frames and combine them into a single multi-bit image with reduced noise and blur, which can be used by the downstream algorithm. We call this scheme quanta burst vision. In this example, the person is successfully detected. Notice that conventional cameras do not always benefit from burst photography, as each frame suffers from a fixed amount of read noise. This can ruin the actual image signal in each frame in challenging low-light, high-speed scenarios. In contrast, SPADs have negligible read noise. Therefore, they are the ideal sensor for low-light burst vision. In this work, we focus on using burst vision to explore quanta vision in the real world. We capture data using a real SPAD array, which are not restricted to one or two proof-of-concept tasks in controlled lab environments. Instead, we capture binary sequences for 9 different downstream tasks, which cover a wide range of lighting conditions, scene or camera motions at various speeds. In addition to indoor scenes, we also evaluate the capability of quanta vision in challenging outdoor scenes. We fix the SPAD camera and the night vision camera side by side above the dashboard of a car, which is driving on a street without any streetlights. The SPAD is able to detect the pedestrian from a longer distance than the night vision camera, even beyond the reach of headlights. We'd like to emphasize that, in the long run, explicit burst reconstruction may not be the optimal approach to quanta vision. Our aim is to use this approach as an example to bootstrap the exploration of quanta vision, which will hopefully spur further research in this young but promising subfield of computer vision.